Good afternoon. Questions? I actually planned ahead today. Yeah, doesn't happen very often. And this is more or less where we left off. You know, we did this, and then it occurs to me that, well, two things occurred to me, right? Suddenly, everyone pays attention when I hand the chalk out. Got that. If that's accurate. What would you say? The other is that you probably don't know how to work through this system very well. Does that make sense? So if I told you to illustrate what happens if you increase ionic strength and you draw it on the diagram. What do you think? So what I have is I have a worksheet for you, okay? And there are two sides to this page. One is the role of pH, and the other is the role of ionic strength. And what I want you to do is to basically draw on the figure, okay? Because I have to need only about half as many of these as I thought I was going to need today. Now, I also brought in blue pens, and you have to use some other colors for red, since red pen, you want a blue pen? Do we need a blue pen?
Are you missing pen?
Yes. Or you can do it in blue pencil. Do you have a blue pencil?
No.
Regular. Well done. Need a blue pen?
You're a color.
We're going to do, there's only blue and red. There's no red. You can't get red at the bookstore.
What? That's awful.
There's another one. Anyone? So, I'm happy for you to work in groups rather than individually. That's up to you. All right, but let's look at pH, role of pH first. Okay, so one is the role of pH. It tells you that you're going to move the pH away from the isoelectric point or towards, the point of zero charge. And the flip side says what happens if you increase ionic strength or decrease ionic strength. All right. So why don't you take 5 minutes or so and draw the solutions on the figure. It says, if you read in the upper left, it says the effect of the change on bulk ion concentration, Nernst potential, double layer thickness, charge decay function, okay, ionic strength, and stable potential. It's the same set of questions on the flip side. Okay, bulk ion concentration, Nernst potential, double layer thickness, charge decay, ionic segregation, and stable potential. Okay, so if the change that you make doesn't affect something, just mark it does not change. Good. But if the change, but then of course draw the rest. And the idea of using colors helps you find these things later. Okay. Good.
have this was like, the intersects this first. Yeah. And then this one. But this one would always be like a linear.
The MF. Oh, he wants to.
So it depends on.
That's what I thought. Yeah. I was
Right.
And no change that happened here, right? No change that happened. I'm better with
Which is fair.
Like the layer is like, do you look the layer like really like on top?
Yeah.
Because it affects this one, this layer. Remember how you said you start down here and then put it up? So then I think this, what is it, not the stern layer, it would be the sheet. That would go in. So then that means. Like yesterday, when I was the purple one. Because this is like the original one and then you do it again, and then you have to start again. And then that changed. Is it what? Yeah.
And he said it's gonna be small.
Smart. We will just do the opposite. So we do that. Where's the right?
Since I get it. The only reason I do that is in this case I have after that. And I took a C plus in past grade, so that's okay, because
We were saying that it's starting here and it's going back to this. But then that would be like, this thing goes up.
So if you want to do it, I'm doing my research.
Yeah, I was saying the same thing when I was taking the now I'm learning it from I don't know if the class action lessons.
You know,
I feel a lot better next to all those outside lines. Understand.
so you have here that your
You can't
those change, but
the way that
just functions, but then you show that their rate change. So it's
still better.
don't
No, no, it's gonna be like, because I have to have time, and it's at the same time, so, but, I have like a, I like have a.
Right, so you have it, right, yeah. I feel like I have right.
Yeah.
Yeah. I don't know, I'm pretty sure the fuse layer is dependent on the multi-atom.
Okay, but the data
Well, this is more of an exercise, I hate this one in particular.
Right, but like, that's how.
She spot checks.
Okay.
Five compounds that are each worth of weight, so if you round it around the spot, you get that whole general. So if you ever go off and get 2 out of 5, ties back to the owner.
So what do you think?
Okay.
Say it again. Yeah.
Yeah, I saw it.
Doing extras? Yeah, because half the buses show up in here. Does everybody want more?
Sure.
Hey, you didn't get one. Oh.
I helped myself.
I'll deliver one to a distance runner.
Well, that's very kind of you. So what?
Not for that, you can add another. So,
I'm not far from something out there. Well, I thought we would go over it. I was expecting more people to show up for class, so I don't care if we get done early. All right. This is the role of pH. Are you ready to do this? Okay, so what happens? So there's a curve that we haven't drawn for a couple of reasons, but typically what you have is we have this curve, which is pH versus zeta potential. This is what's most common that you see. Okay, that curve looks like this. Good? Okay. What you don't see though is this curve, typically pH versus Nernst potential. And this curve has kind of a funny shape to it. It looks more like this, which is why I don't draw it for you. because I think it becomes confusing. Okay, now ideally, what would happen is, slightly skewed world, those two lined up. Okay, and that means we are what? What does that mean if they line up? Yeah, IEP and Z potential are the same, or the point zero charge is the same, meaning that we are, what's the condition?
Oh, there's no, indifferent electrolytes.
It is an indifferent electrolyte. There's no specific affinity, right?
Yeah.
So you're in the presence of an indifferent electrolyte if those line up. And we would assume for alumina that this value is about 8.5. Good? Okay? So, you have a condition listed on the page, and you don't know anything about the condition except for what? Where's the pH that I started at? Okay, this is a great question. Go ahead. No, pH I started with in this figure.
It's somewhere away from the zero charge because
Okay.
you have to be able to move towards or away from it.
It's away from the point of zero charge, and which direction? You thought you were in the clear. You're not. Huh? It is away. But I'd say which direction, we could argue for left or right in terms of the figures drawn on the board, right? Or we can argue for increasing acid or increasing base, right? So which direction is it? Is it increasing acid or is it increasing base? How did he get to increasing acid? Is what? Yes, but there's a sign on the Nernst potential, correct? What's the sign on the Nernst potential? It's a stated condition of the question on the spec for a positively charged particle, right? And I drew pluses in here that you may or may not be able to see, but it's a positively charged particle. That means that you must be at a pH below the point of zero charge, right? Because as we shift to a lower pH, we develop a positive net charge on the particle surface. So what you know is that the conditions that we started with this figure are somewhere south of the point of zero charge. Okay, so this is the PZC, and this is the IEP, and you will need to know the difference between the two. And where this figure started, okay, and it is an illustration, right? Where this figure started was someplace south, okay, someplace below the point of zero charge, right? Because you have a net negative or net positive charge on the particle surface. Does that make sense to everybody? Okay, so you know where you started in the system. Then the question is, what happens if the pH moves away from the point of zero charge? So what does that mean? I'm going to move further acidic, right, further to the left, and therefore I'm going to get an increase in positive charge. I'm going to go get my colored chalk. So you may. I'm going to review what you've done and see if you got it right. Is this helpful? Okay. So you're up. All right. Yeah.
So we're gonna see the box.
Oh, I get it. Okay, so.
So, what happens?
If you move away, you go to right.
It'll increase. The nerve potential and the zeta potential will both increase.
Okay, so if I find red, which I have here, all right? So what we do with red is we're gonna come over here, right? Good? So I'm moving the pH further to the left by definition. Now, if we had started off with a negatively charged particle, I would be moving the pH further to the right, or increase basicity, right? So if I do this, what has to happen is that the charge on the particle surface goes up and the zeta potential goes up. So on this figure, right, we have this. pH moved away from the point of zero charge. My nerve potential increases. Good? Then what happens? Oh, let's see. Bulk ion concentration change?
Nope.
Nope. No change. No. All right. Let's do that. Okay. Nernst potential increased. Done. Okay. Double layer thickness?
No change.
No change. Okay. Next. Charge decay. Oh, it has to do this. No change in double layer. That means I end here at this point. This comes down like this. Basically, it should be a straight line here because of the approximation. And then it's going to come down like that. Good? Something like that. Good? I figured out I could draw this figure bigger. We used to do a smaller figure. It's hard to use this as bigger. Therefore, easier. Okay. What else? Oh, zeta potential. Oh, ionic segregation. That's here. No change? Change. No change. No change. Okay. Last, zeta potential increases. So here's my zeta potential. And this is zeta red. Okay. Are we okay with that? Is this helpful? Someone want to attempt the blue? All right. This is ink, by the way. Are you going to use your page, right?
No, let me go look at mine, so.
Oh, no, you're not.
Oh, well. Okay, so I'm actually gonna, start down here.
No, you're not.
I'm not, why?
What do you do first? Okay, walk me through it.
Why I wanna start down here?
Just do it.
So I'm gonna start down here because first of all, we know that our concentration of ions are not changing.
Okay.
So because of that, this point doesn't change either.
Good.
How
How about bulk ion concentration?
not changing.
Okay.
Now, so we're just changing the pH, not.
And we're moving the pH.
That's why all that stuff is that.
How are we moving the pH?
We are moving the pH toward the point of zero, oh, I don't remember what it's called, but zero concentration.
Zero charge.
Zero charge.
Blue. Good.
So, from those graphs, in both cases, the zeta and our terms go down.
Do not mark the zeta first. Why not? It's a function of that decay function, right? And you need to anchor that decay function first by marking the Nernst potential. Good. And the Nernst potential here will decrease away from where it started at. So you may mark where it ends up.
For, for
Nernst potential.
So I'm gonna go here in a little bit. Yeah.
Okay? Are you all okay with that? All right. Now what?
Next we draw our line.
Good. And then?
Here's our zeta. So
Good,
our
good.
nernst goes down and the zeta goes down. Any arguments?
Are we okay with that? Thank you. Is this helpful?
I won.
You must savor the small victories.
Yes, indeed.
Okay. Are we good with that? Everybody good? Is this helpful? So now we're going to flip the page over. Rule of ionic strength. So, here's a really good question, right? So you recognize that this plot down here on the bottom, the Nernst potential, is about the reaction of that particle with water. Okay? And so the thing that you should pay attention to is this. This here, okay? This tells you the reaction on the particle surface, right? How that particle surface reacts with water in the presence of acid or base. This is just the chemical reactions at the surface of the particle. There is no ionic strength information incorporated into these reactions. Are you all comfortable with that? Okay, we don't have a salt in there that changes concentration when you add acid or base into the system. You don't have something that says, oh, I have sodium chloride in here dissociating blah, blah, blah as a function of pH. You don't have that. Fair? Okay? So what you should surmise from that is that there will be no change in ionic strength. You may argue that that may not be 100% true, but that is a very good place to start. And over a broad range of pH values, changing the pH does not significantly change the ionic strength. It's only when you get out to the edges, okay, we have to add a lot of acid or a lot of base, and you see a significant change in ionic strength. Good? That means we go back to this figure here. This figure does not change, does it? What does change? The zeta potential changes, okay? The zeta potential changes because we increase ionic strength, or decrease ionic strength, so the top one is increased, we go to red, okay, we compress the double layer. But what should happen is that the Nernst potential should not change, right? So in both cases, okay, actually we kind of, all right, so what happens to the Nernst potential when I change ionic strength? It stays the same. So we'll say that this, we'll put the red dot there, and we'll say no, Nernst potential here. Good? Now the rest of it, what happens? Oh no, wait a minute. I'm increasing ionic strength. What happens to the bulk ionic concentration? So case A is increased ionic strength. What happens to the bulk ionic concentration? It increases. That is exactly what I'm doing, right? I'm increasing the bulk ionic concentration. Good. So we're going to draw that in here. I don't care if these things overlap. We're going to draw it in here this way. We're going to say, here's my bulk ionic concentration associated with an increase in ionic concentration. Good. Okay. What does that do? Let's see. There's potential doesn't change. Double layer thickness. Let's do that in a minute. Okay. So first, let's do charge decay. Nope, let's do ion segregation. So ion segregation, you might assume that this point is fixed. It's going to come up to something like this. Okay, it's going to come down like this. Good with that? What that's going to do is that's going to translate up this way. Everybody okay with that? Okay, then what happens? Oh, let's see. Then my decay function has to terminate at this point here. Okay, so it's going to come down like this. Straight line typically first. then it would decay. So my zeta potential now decreases to here. And if you want to go up to the top, you can do this. Understood? I forgot to ask a question on this little blurb at the top. What did I forget to ask? What a good question. I'll have to add that in there next time. What happens to the stern layer? It stays the same, right? So the assumption is that that absorption of ions at the particle surface is fixed. The number of ions that will be strongly held to the particle surface is fixed. And so that stern layer always remains the same. So in all four cases here, the stern layer will not change. Are we okay with that? Okay? So that means that my zeta potential decreases. Okay? My Nernst potential is unaffected. Okay, so this is down. Okay? And my stern layer stays the same. No change. I'll put a no here for that. Right? And then my diffuse double layer L decreases. Okay, so the diffuse layer is smaller. But this is L. Okay? Charge segregation changes. And then I end up with a decrease in zeta potential. Are we okay with that? Okay? So if I were to do that on this figure with the red chalk, you get this. Good? Are we all right with that? Okay. So, we have one more to do. Someone wish to do this one? Okay, so show that in the bulk ionic concentration.
So bulk ionic concentration, does that get smaller because it's will only go out to here?
No, keep going. You're talking about the bulk ionic concentration. So it goes past the double layer. Just draw a straight line, right? Okay. And then you could decide, you already drew your double layer at the top, right? But it actually goes out to where that blue vertical line is, right? Okay. Fair enough. You have a problem with overwriting letters that I put on a piece of paper? Can't do that.
I like reading.
Yes.
What happens to the Nernst potential?
So the Nernst potential will stay the same. So
Okay.
it'll also start here.
Yeah.
But it'll be turning here instead.
Correct?
So it'll have much larger source. So zeta potential.
Draw the zeta, put the line on there for the zeta potential. Show the value. Good. Are we okay with this? Does this help?
Yes.
This was fun. We should do this more often.
I think they call it active learning. I'm resistant to it. Good. Okay. So here on this figure, Nernst potential, no change. In this case, your curve does this. Good? Any questions? To be kind to the people who couldn't seem to find their way here today, I'm not going to cover new material. We will throw the towel in for the first half of the semester. You good? Okay? Any questions? Then we are done for the day. Great. Enjoy your break.
Do you want your piece back?
Nope, you may keep my pen. The cheapest pens we could buy, so.